Hello geometry friends, it's Mr. Vass here, and we are about to dive into section 533, the law of cosines. And before I do any of the problems from this section, I'd quickly like to summarize where we've been so far. So let's take a look at this here. What's in our triangle toolkit so far? Let's talk about what we've done to date. Well, we have the triangle angle sum theorem to find missing angles in a triangle. If we know two of them, we can find the other one because they have to add up to 180. And all of these things I'm going to talk about are tools that help us find missing measurements in triangles, side lengths or angle measures. What else? Well, we have the Pythagorean theorem to help us find missing sides in a right triangle. And again, that one is specific to right triangles. Pythagorean theorem. There it is, folks, spelled out for you because I know you can't spell it or pronounce it, many of you. So take a mental picture of that so next time I ask you to spell it, you can do that. What else do we have? Well, we have trigonometry. That's exciting. We have sine, cosine, and tangent. And all of these things are ratios. And I think ratio is an important mathematical word. So that's one, if you don't know what a ratio is, you might want to look that up right now. Okay, so trigonometry, we have sine, cosine, and tangent. Those are trig ratios. And if we're looking for side lengths, we would use the regular version of these trig ratios. If we're looking for angles, we would use the inverse of each of these to find a missing angle measurement. So again, toolbox is getting pretty full here. What else do we have? Well, we got special right triangles, the 30, 60, 90, and 45, 45, 90. That's just really a shortcut. Okay, that's a shortcut to help us save time. If we see those angle measurements, we can say, hey, I know a lot about the side lengths just from those special triangle angle relationships. We also had Pythagorean triples. Pythagorean triples were another shortcut that just the Pythagorean triple is when the three sides of a right triangle are all whole numbers, and we were able to use those again as a shortcut. Last but not least, we have the law of sines, and that one is worth talking about in a little more detail because we just covered that one recently. So the law of sines says the following. If you have a triangle, and the law of sines works for any triangle, so that's worth noting, works for any triangle, not just the right triangle, any triangle, doesn't matter what the angle measurements are. Okay, works for any triangle. And the law of sines said this: if you have a triangle, the sine of angle A divided by side A is equal to the sine of angle B divided by side length B. And I just want to do a quick example to kind of show you how this works. By the way, I didn't like that S. We're going to clean that up for you because you deserve the best. There we go. All right, so let's take a look at. I have a triangle here. Why not? Let's just add some measurements here. So let's call this. This looks like about 50 degrees, and we'll call this one 35 degrees, and then we'll call this. Oh, how about the number 6? That seems like a reasonable number. And how about X? So here's my question. I have this formula that says the sine of A over little a equals the sine of B over little b, and I don't have anything labeled as A, B, or C in this triangle. Does that mean you can't do the problem? Absolutely not. Okay? So here's how this works. This A, the angle, is across from the side length A. 50 degrees is across from the side length of 6. So that's going to be the first thing I write. The sine of 50 degrees divided by 6. Now let's see what the other half of this proportion says. Angle B is always across from side length B. So that means I've got, well, this 35 degrees, that's across from X. So the other half of my proportion is going to be the sine of 35 degrees over X. Now, through the magic of algebra, you can take this proportion and rewrite it as X times the sine of 50 equals 6 times the sine of 35. But wait, there's more, because we want to solve for x. So how do we solve for x in something like this? Well, we're going to divide both sides by the sine of 50. The sine of 50 is just a number. It's going to cancel from that side. If I divide the left side by sine of 50, I better do the same to the right side. And then we have this. X equals 6 times the sine of 35 degrees divided by the sine of 50 degrees. And that's, I mean, we would never leave our answer looking like that. We would go to our calculator and see what that equals as an approximate decimal. So let's do that right now. So let's flip over the calculator and see how we do this. We're going to start a document here, and we're going to just need the calculator. So we had 6 times the sine of 35 degrees and we had to divide that by the sine. Just so I don't get the right number, let me flip back here. We're going to divide that by sine 50. Sine of 50 degrees. And we grip it and rip it in the calculator, and we get an answer of 4.4925. So we're going to just call that 4.49. And there's our answer. 4.49 is the value of x. Now, remember, why did I show you this example? Well, the way we learned law of sines in our notes was sine of angle A divided by side length A equals the sine of angle B divided by side length B. But we were given a triangle that wasn't labeled. Okay? I just wanted to show you that this works. It doesn't matter if the triangle is labeled or not. It doesn't matter what you call A, B, C, D, E, or F. It absolutely doesn't matter. As long as you have a triangle where you know an angle and the side across from it, if you know the other angle, you can find the side across from it. Okay? And one other thing worth noting here is I didn't write this in the notes yesterday, but take a look at this. I can extend this to the other side as well. This is actually an extended proportion. If I wanted to find this side length here, I could find this angle and just use the same equation. Okay, so that's a review of what we've done so far with triangles. What are we going to learn new today? Well, today we talk about the law of cosines, and you'll notice this is problem 5-96 from your textbook, and I'm actually going to derive the law of cosines for you, and I'm going to do it in my own order. If you look in the book, it kind of steps you through it in steps A through D of this problem. But just go ahead and take a look at what I'm about to do here, and hopefully you can follow along. All right, so the first thing I'm going to do is I'm going to look and say I've got a triangle here. It's just a general triangle, but it's split into a right triangle on the left and another right triangle on the right. Okay, so I'm going to first look at the left-hand side of this triangle. Okay, so I'm going to start by saying let's look at the left-hand side. So the left-hand side, I'm going to write down every equation I can think of. Well, first thing I see is that I have some side lengths labeled. Okay, so I'm going to go with the Pythagorean theorem, and I'm going to say, yep, the hypotenuse squared equals a leg squared plus the other leg squared. So I have a squared equals x squared plus y squared. I'm also going to take a look at angle C down here, and I'm going to write out the ratio of the cosine of angle C. And let's see, cosine is adjacent leg over hypotenuse, so that's equal to x over a. Okay, I'm going to just stop right there for the time being, and now I'm going to go over and look at the right-hand triangle. So let's go ahead and look at the triangle on the right. We're going to do some similar things with the triangle on the right. Well, first thing I'm going to do is look at the Pythagorean theorem. So I have hypotenuse, which is c. C squared equals leg squared, which, well, I have one leg here that's y. So hypotenuse equals leg squared plus. So now here's where I run into a bit of trouble. Okay, the other leg in this triangle is this guy right here. Okay, that guy right there. And that's not labeled. But I think what I can do is I can say that this length right here is going to be b minus x. And I hope you can see that because the entire distance from C to A is called b, but then I have this little distance here from C to D, which is called x. So the distance from D to A is b minus x. That is the other leg in the triangle. So I have to take b minus x and square it. Notice I put that in parentheses because I can't just square b and x and then subtract the 2. I have to do the quantity b minus x squared. And if hopefully you remember this little trick we've done here to multiply two algebraic expressions like this. I can set up a little generic rectangle, and I can say b times b is b squared, b times negative x is negative bx. I also have b times negative x here, which is negative bx. And then I have negative x times negative x, which is positive x squared. So when I take the quantity b minus x squared, I get the sum of these four boxes. So let's go ahead and simplify that. C squared equals y squared plus the sum of these four boxes is going to be b squared. And then I have two of these minus bx's, so it's going to be minus 2bx and then plus x squared. Okay, so hopefully you're following along here, and I got to see what I can do next. Well, the next thing I'm going to do is I'm going to rearrange some things on the right-hand side here. I'm going to take this x squared and move it up with the y squared. So that's going to be c squared equals x squared plus y squared. And then I still have plus b squared minus 2bx. All right, well, here's the first time I'm going to do something that's a little bit crazy. Take a look at this. I got x squared plus y squared here. I don't know if you noticed this. There's an x squared plus y squared over here. And that equals a squared. So I'm going to do that substitution and rewrite c squared equals a squared plus b squared minus 2 times b times x. Now, folks, what is starting to emerge here is the law of cosines. And I want you to take a look at this. Right now what I'm saying is c squared equals a squared plus b squared and then minus this other thing. It kind of looks like the Pythagorean theorem right now. Not exactly, but it kind of does. Let's see what happens next. Let's take a look at this. I've got x right here. But I also have an x over here. So let's see what happens if we rearrange this. Through the magic of modern technology, I'm going to rewrite this as x equals a times the cosine of angle C. So I can now use this version of x and substitute it into my equation. So that equation now becomes c squared equals a squared plus b squared minus 2 times b times a times the cosine of c. Folks, we're almost done. The last thing I'm going to do here is just rewrite it in a more convenient form. C squared equals a squared plus b squared minus 2 times a times b times the cosine of c. Folks, give yourself a little pat on the back, because what you just did is you, through the help of this video, you just derived the law of cosines. This is the law of cosines. And that's really exciting because it works for any triangle. Not just right triangles, it works for any triangle, and that is really, really exciting. Okay, so that is problem 5-96. We just derived the law of cosines. Now let's go ahead and take a look at a problem here. Find the side length x, and I'm going to write the law of cosines here again. C squared equals a squared plus b squared minus 2AB times the cosine of C. And you'll notice in this triangle, folks, even my dogs are excited about the law of cosine. So let's hold on a second here and see if we can't simmer them down. Okay, order has been restored. Let's go back and take a look at how on earth can we apply this formula to a triangle that doesn't have any sides labeled, doesn't have any angles labeled. Well, let's go back up here and look at the original triangle we had and compare it to the law of cosines. So I said c squared, law of cosines, c squared equals a squared plus b squared minus 2 times ab cosine of c. So if you can follow that pattern, you can use that anytime you have two side lengths, the angle between them, and you're looking for the side opposite of them. So this is going to be equal to c in our law of cosines formula. This is going to be equal to a. This is going to be equal to b. And this is going to be angle c right here. Okay, so let's see how this works. C squared, which is x squared, is going to equal 6 squared plus 7 squared minus 2 times 6 times 7 times the cosine of 120 degrees. Okay, so let's go ahead and run through the numbers here. And you got to be really careful here, folks. Students make mistakes all the time here. Remember, the order of operations says you have to do multiplication before you do addition and subtraction. So all of this has to be multiplied together first. Don't forget to multiply this first. So many times I see students do 6 squared plus 7 squared minus 2, and then then it's screwed up. Okay. So again, make sure this all gets multiplied together. If you know how to use your calculator, you don't even have to worry about that because your calculator knows the order of operations. Here's what I mean by that. So we have 6 squared plus 7 squared minus 2 times 6 times 7 times the cosine of 120 degrees. Okay, so again, if you're doing this calculation in little steps, make sure you multiply all of these first before you subtract them from 6 squared plus 7 squared. We grip it and rip it, and we get an answer of 127. Okay, that's really exciting. So that's 127 right there. And then some of you are going to be like, yay, we're done, let's go home. But this is not the final answer. Okay, if x squared equals 127, that means x equals the square root of 127. Oh gosh, don't forget that last little step. And now let's see what that equals as a decimal. So the approximate decimal there is square root of 127 is about 11.269. Congratulations, folks. You have now learned a new triangle tool, the law of cosines. Let's see if you can use this plus the previous tools we've learned to apply and solve triangles on the back side of the notes. So question 5-97, we've got 3 different triangles here. I'm going to go ahead and solve each of these, but what I want you to do is I want you to press pause and try and do them on your own first. All right, folks, let's take a look at this one real quick. I used law of sines. How did I know that I was going to use law of sines? Well, one of the clues that I look for is anytime you have an angle measurement and you know the side length across from it, you can use law of sines. Okay, that's one of the tricks that I look for. 4.95, I just want to talk about why this answer makes sense. So of these two angles I have, 35 and 20, 35 is bigger than 20. So this side length across from that should be bigger than the side across from 20. And sure enough, 8.3 is bigger than 4.95, so that's a good thing. That means that gives me a little sniff test there that says, yep, my answer smells okay, I think I'm going to move on. Okay, for this next problem, we are looking for an angle inside of a triangle. Let's see how we're going to do that. Okay, folks, this was a tricky one. I know we haven't done this a lot, but to find a missing angle inside of a triangle, if it's a right triangle, we can use inverse trig to do that. I know that the tangent ratio of this angle x, tangent ratio, remember, is going to be the opposite leg divided by the adjacent leg. The tangent ratio is 5/9. So I can't plug this version into my calculator, but this version I can. So what does this do? It goes and looks up in a trig table 5/9 as a ratio and figure out what angle that matches with. And I'm going to be honest with you, folks. That approximately equal to sign right there, I am just not happy with it. You deserve better. Let's go with that. That's a little better. Okay, so that's it for this example problem. We got another one to go here. Let's take a look at example C. There you go, folks. There's the side length x, and what I can't emphasize enough is that when you use the law of cosines, make sure you unsquare that number you get at the end, take the square root of it, so that you find the side length, not the side length squared. And just as a quick little sniff check here, 16 is a pretty small angle. In fact, it's probably the smallest angle in this triangle, and we found a side length that is smaller than the other two, so that's good. That makes a little sense for us. Now, if at this point you're feeling pretty overwhelmed, go ahead and stop the video, maybe get some tissues out, kind of clean up the tears a little bit. But I'm going to move into question 5-98, and this is really a bonus. Okay, this is a bonus, and so I'm going to go through this quickly, and this is really for the big boys and girls out there that want to learn some advanced trig here. And what I'm going to use is I'm going to use the law of cosines to find angle alpha. And here's what I'm going to do. I'm going to call this A, and I'm going to call this B, and I'm going to call this C, and that means this would be C over here. But now angle C is actually called alpha. So let's take a look at this. C squared equals A squared plus B squared minus 2AB cosine of C. So let's take a look at what we get. There you have it, folks. That's a little bit of advanced trig there. We just found an angle measurement when we knew the three side lengths in the triangle. And I used the law of cosines to do that. So what I did here was I got to this step, and I found that I had a bunch of numbers, and cosine of alpha was still just a symbol. So what I did is I solved for that symbol by subtracting 64 and 49 from both sides and then dividing both sides by negative 112. And that simplified to this, 13 over 112. Well, if the cosine of alpha equals 13 over 112, that means alpha equals the inverse cosine of 13 over 112. And this I plugged into my calculator to get 83.3 degrees. Hold on one second here. Let's see what we got for part B. So part B of this problem says solve for the other two angles using any method you want. And I'm going to go ahead and jump through that real quick, and hopefully you can follow along. There you have it, folks. Just solve for the other two angles in that triangle. One in the upper left-hand corner is 52.6. Upper right-hand corner is 44.1. There are multiple different strategies you could have used to find one of those angles. That was just the strategy I chose. So, okay, folks, I hope you found this video fun, engaging, rewarding, and educational. Thank you.